So welcome everyone to the Starknet Foundation Developer Basecamp Session 2. Today we'll be discussing Starknet and Layer 2s. And just for people who started to join today, we are a 3-people group to help you on this Developer Basecamp journey. So we have David right here, who is the main teacher of the Basecamp, and he will be teaching all 6 sessions. I'm Sitong, and I'm also from the Starknet Foundation team working with David. And if you have anything about agenda, program, recordings, or anything, feel free to reach out. And right here, we also have Truth, who was actually a graduate with honors of our previous Basecamp in May. And now he's joining us as a teaching assistant, and he will be answering your questions during the class. And just a quick recap as well. We have the Basecamp graduation is based on points. So we have a scoring system for graduation. So in maximum, you can get 60 points for a graduation. And you can get it, for example, from quizzes. We have live quizzes for each session. So at the end of each session, we have a 4-question quiz. And to get each question correctly, you can get 1 point for the question. And we have 5 mandatory sessions from today to session 6. So in total, there will be 20 questions, and you can get maximum 20 points for quizzes. One thing to remind you is that the quiz can only be taken live during Zoom. So if you watch a recording, you may not be able to get the points for the quiz. And you also don't have to panic about the quizzes, because it's not to make your life super hard. The questions will all be covered in David's presentation during class. So as long as you pay attention, you will be able to answer them. Another 20 points you can get is from homework. So homework is rather easy. You just follow live coding that David presents during the live classes, and then you publish the same code to GitHub, and then we'll send out a form to collect your GitHub link. So the homework, now you don't have to worry, because from session 1 to session 3, we don't have live coding, so you don't have to do any homework. So the homework you can start from session 4. So we have a lot of people asking that questions. So just to clarify. And another 20 points you can get is by Starklinks, doing Starklink challenges. So Starklinks is like an interactive platform where you can learn more about Cairo, and then you connect your GitHub handle with Starklinks, and then you complete all the challenges by coding. So that is how the interactive way that you can polish your Cairo skills. So to recap, in total, we have 60 points divided into quizzes, homework, and Starklinks. And in order to graduate, we have 3 status to graduate from Basecamp. You can be either an attendee, a graduate, or a graduate with honors. And if you want to be an attendee, you just need to attend 25% of the live classes from today to session 6, 5 sessions in total. You join 25%, then you are an attendee. But if you want to be a graduate, you not only need to attend more than 50% of the live classes, you also need to get more than 30 points out of 60. So in total, you have 60 points. And if you get 30 points, you can be qualified as a graduate. But if you want to be a graduate with honors like Truth did in May, then you need to attend more than half of the classes, and then you need to score more than 48 points out of 60. Okay, and then we have to go through this really fast, because we covered it in session 1, and we have a lot of things to cover in this session as well. So if you have any questions, you can drop your questions in the QA box in Zoom. Please don't drop it in the chat, because there are lots of chats going on. We might miss it. And at the end of the session, when we upload the recording, we will also export the QA chat history, so you can see the answers that we answered during the class. And for technical questions, you can also share your questions in the Basecamp channel on Discord. We will answer you. And then for general questions, you can post it in Discord as well, or email me directly. And it's important to check out the resource page, because we publish all the slides, the recordings, the useful links. You can find Starknet links there. A lot of our social media links, everything you need it, you can find it on the resource page. And one last reminder is to be aware of scams on Discord. So when you are interacting with people, especially with our team, like Truth, David, or me, please make sure that it's us that you are really talking to, because there are lots of scams out there. So be careful.
So then there's a question in the Q&A where we can see our points in total.
Yeah, because we will start a spreadsheet that is public, where everyone can see session 1 quiz, session 2 quiz, session 1 recordings, how many minutes did you attend each session. We can track it from the Zoom dashboard. So we will publish a spreadsheet publicly, and everyone can track it every week, your progress there. We haven't published it yet. We'll publish it next week probably, because session 1 is optional, so that the quiz points and attendance is not taken into consideration. So
I just shared the link to the Excel, but it's fine, because it only has session 1, which is optional. It's going to really matter.
I have a link ready though.
Yeah, I put it in the Q&A.
You put it ready. Okay, cool. So today, as I mentioned, we have 6 sessions in total. The session 1 is an optional session. We talked about Bitcoin, Ethereum, and today we'll dive into Starknet and layer 2. And we have a lot of exciting things to share. So I'm going to pass my mic on to David. I'm going to stop sharing so you can share.
Thank you, Sutton. Thank you for the intro to the session. I'm going to share my screen now. Here we go. Close this. Okay, just 1 second. Just configuring my own view so I can see the Q&A and the chat while I'm talking to you. Okay, good. All right. We were here, right? Yeah. So before we start, I just want to clarify some notions about StarkWare and the Starknet Foundation, some differences, because you're all here to really learn more about learn more about Starknet, the blockchain. But there are 2 organizations behind Starknet that you need to be aware of. The first one is StarkWare. And StarkWare is a company, and as any company, it's a for-profit company. And it's basically the company who's behind all the research and development, or at least most of it, of Starknet, right? Like all the math behind validity proof that was created by StarkWare, like the fundamental research, then the implementation, like Cairo as a programming language in Starknet. So they are really the main driving force in the engineering side of Starknet. Then you have the Starknet Foundation that we in Zutun work for, which is a non-for-profit organization. And the goal is really to expand the ecosystem through educational activities like this one, through things like hackathons, meetups, hacker houses, startup houses, as we call it today. So this is part of one of the efforts to try to grow the ecosystem. We also have a grant program to support builders and entrepreneurs who wants to create Web3 apps on Starknet. So with that out of the way, you know that there's 2 entities, because we're going to be making references to them as we move along. All right, the topics for today. First of all, we're going to do a quick recap of session 1, which was an optional session. So if you didn't attend, that's fine. We assume that you already know the basics of how Bitcoin and Ethereum works. Then we're going to talk about how to scaling Ethereum, or the whole history of scaling. Then we jump into verifiable computation, which is essentially to talk about Cairo at this point. Then we move on to validity proof, which is like the secret sauce behind Starknet. Then we're going to have a break, some coffee break. Then we go back and jump to talk about smart wallets. And then I'm going to show you how to do the setup of a wallet on your phone very quickly. And finally, we're going to talk about some of the plans about the upcoming integration with Bitcoin and some of the different ways we can make that happen, some of the benefits as well. And as you know, we're going to close with a quiz, 4 questions. And this quiz is going to be part of the graduation requirement for Basecamp, as Sutun just mentioned before. So quick recap about session 1. So we discussed about Bitcoin and Ethereum, right? We did a comparison of both. So in terms of being programmable, Bitcoin is not programmable. All the programs that exist in Bitcoin are hard-coded into the protocol. So anytime you want to add a new program, then you need to do what's called a soft fork. In the case of Ethereum, the whole point of Ethereum is to be a programmable platform, almost like a programmable computer that anyone can create their own program in the form of a smart contract, put it on Ethereum, and anyone can execute it. And you write this code using Solidity or using Viper. Those are the 2 high-level languages you can use that it compiles to the EVM bytecode. Then about the consensus, we discussed that Bitcoin uses what's called the proof of work, and we discussed how proof of work actually works under the hood and with the hashes and all that. But then Ethereum went a different path, which is much more energy efficient and actually uses more like economic incentives to keep the network aligned. That is called proof of stake. We also discussed how that works. When it comes to handling the internal state of the blockchain, Bitcoin is considered to be a stateless machine just because it uses the UTXO set, where you have to manually collect all the UTXO of a person to know their balance, while Ethereum behaves more like a normal computer, or like a state machine, as they call it, where it actually stores the state or the balances of any person and any smart contract in this big Merkle-Patricia trie that we also discussed in session 1. So it is a stateful machine because it directly stores balances. Now, when it comes to storage, in the case of Bitcoin, it uses a mix of a key value database for the UTXO and the Merkle trees for the information within each block. In the case of Ethereum, we actually rely on pretty much one gigantic or multiple, actually, Merkle-Patricia tries. In this Merkle-Patricia trie, it's like an improvement over a Merkle tree to make it work not only with the benefits that a Merkle tree gives you, but also to work as an effective database as well. And finally, important difference is the energy usage. Because Bitcoin relies on proof of work, the energy usage is very high. There's a lot of computing power on the network trying to solve the POW. In the case of Ethereum, because it's based on economic incentives, the energy usage is actually very, very low. So we can say it's almost negligible. That's it. That's what we discussed session 1. Now we can actually go with the new content for session 2, which is scaling Ethereum. And let me tell you a story for those of you who are new to the blockchain, to Ethereum, and this is about CryptoKitties. And that's how we actually came to realize that we need to scale Ethereum in some way. So what happened that at the beginning of Ethereum, when it came online in 2014, 2015, there was a lot of excitement from people already in the node, but there was not a lot of demand for Ethereum itself, right? And because there was not a lot of demand, the gas was cheap, right? Gas is this, we discussed session 1, is this way to measure the usage of this global computer. And if the gas is cheap, it means the transactions are very cheap as well. Only like a few cents to send a transaction on Ethereum. So people were happy, just trying things, experimenting. What happened is that in 2017, this new collection was launched. It's actually, it was the first time I think the ERC 721 NFT was invented and put to use, because the first NFT collection was launched, called the CryptoKitties. Maybe not the first, because we also have the CryptoPunks, but the first time the actual NFT smart contract with ERC 721 was used, and CryptoKitty appeared. And the game was about not just trading funny cats, you can also breed them. And by breeding them, you can actually create like new cats that was going to make some of the traits of the parents. So that game in that trade became so popular overnight that just that smart contract started to consume 50% of all of Ethereum by itself. That caused what's called a bidding war. So because now block space was used, or demand for Ethereum was so high, people were pretty much competing against each other to have priorities to send their transaction, or to actually get their transaction included in the block. That actually made the cost per transaction to spike, because the gas also spiked. So now we went from only a few cents per transaction to about $3 per transaction. Which back then was unheard of, was crazy. And people were up in arms, it's impossible. All the networks slowed down to a crawl. Many of the systems, it was like a stress test of Ethereum. And that's the first time I think we all collectively realized, okay, Ethereum needs to keep improving its capacity because demand is coming. And if we thought $3 per transaction was expensive, there was a second wave of NFT collections in 2021 that actually saw a spike even higher of $100 per transaction. And it was completely crazy. Pretty much a lot of people got priced out of using Ethereum. It became so expensive and so congested that it was clear that we needed to find a way to scale. So this congestion was so bad that for the most part, the network was unusable, right? You have to wait. If you were not willing to pay $100, you had to wait a long time for your transaction to be included. And that was just very bad UX. So this was the topic of the different paths that Ethereum or the community approach to try to prevent this and have more block space. So the question was, okay, how do we scale the network? One option, and a simple one, will be, well, what if we just turn up all the requirements for a full node? It makes it more powerful. Let's make it more memory, more CPU, more everything, more bandwidth. And that's one way, right? Instead of having this very low demands for run a full node on Ethereum with an expensive machine, Which is the benefit of doing that way is that it's highly decentralized, right? It's very cheap to spin up your node and run Ethereum at home, which creates a network that is very robust and very secure, but it has the downside that it's not very scalable, right? It cannot handle that much traffic because the requirements were very low on purpose. So of course, one option will be, well, what if we just pump up the requirements and just say, hey, if you want to run a full node, now you need to have a computer with these very high specs, crazy numbers, like 10 gigabit internet connection, which in practice, what it will give you is a network with fewer nodes, but way more powerful, each one of them. But the downside is that the network will be less decentralized because not everyone has access to not only the money to run build this machine, but also has access to the infrastructure. Like if you don't have like a 10 gigabits per second connection to the internet, then you just can't. And a less decentralized network is a network that is first less reliable, right? Because there's fewer nodes to actually execute transactions in case someone else failed, but also less secure because there's a higher chance of collusion between stakers to attack the network. Of course, this decision was at that time like scrap. We're not going to go this way. It's not worth it, the trade-off. But that's essentially the path that many blockchains follow, right? Solana being one of them. It's just the requirement for right now Solana node is extremely high, and you see the same with the other networks. So this is one way to scale, right? Let's call vertical scaling. This is not the path that Ethereum followed because we didn't want to sacrifice security and reliability. Now, the other option discussed and the option that actually we went for is to scale with layers. And the way you will do is that you will now consider to be Ethereum to be like the layer one, like the settlement layer. It will remain roughly the same with a few tweaks. But then now you will have what's called layer twos, right? In this layer twos they're usually called rollups. Not every layer two is a rollup, but every rollup is a layer two. And this will be like a specialized blockchains that they will settle data to Ethereum. For example, Arbitrum, Optimism, zkSync, Starknet, there are many more, all of them layer twos. And what they will do, basically, okay, so these layer twos, they will have each one of them more higher computer requirements, more powerful machines, but they will still use Ethereum for their security, right? Because at this point, all of these layer twos are centralized. And the fact they're centralized, it doesn't mean they're less reliable because it's a single machine that if it fails, the network stops for some of them. Some of them have actually mechanism to avoid that. But also, it doesn't affect the security because now their systems are using Ethereum as their security layer in a way, right? So you get a very good trade-off between the two of them. The main node that is run for each one of these projects, for which one of the layer two is actually now the sequencer. And the sequencer is the node that is actually creates the blocks for the layer two, the nodes for Ethereum, and then does some magic for settlement on Ethereum. Now, there are two families of layer twos or rollups. One of them are optimistic rollups. For example, Arbitrum, Optimism, Base. There are more, I just forget. And then you have the family of the zero knowledge rollups. You have zkSync, you have Starknet, you have Scroll, you have others, I forget now. But that's the family that we're going to be interested today, right? Zero knowledge. Another difference between these two different rollups is that the majority of them supports the EVM, or at least a version of it, not exactly 100% the same as Ethereum, but close enough that you can deploy the smart contract that you have on Solidity, you can deploy it on layer two, except for a Starknet and a few others that instead of using the EVM, Starknet uses what's called the CVM, or the Cairo virtual machine. And we're going to take later why we went this path of creating our own virtual machine that is different from the EVM that requires its own programming language that is not Solidity. So the pros of scaling with layers, first of all, you get the high performance, right? So that's the whole idea, just to be able to manage more traffic. But then you have the security of Ethereum, right? That's the really good benefit. Like you don't sacrifice security because you're actually working in tandem with Ethereum for this purpose. Now, the cons of doing this ways is obviously centralization. Right now, all these layer twos are centralized, even Starknet. Starknet is doing very strong steps to decentralize, but it will take a while to get to the point that you get reliable decentralization. But also other issues that you get fragmentation, because all these blockchains, they live in they have their own internal state that is detached from each one of them, and it will even detach from Ethereum itself. So you create this all like a closed environments that they can communicate with Ethereum in some capacity, but they're not really Ethereum, right? So you get benefits, you get downside, but it was better than just simply sacrifice digitalization and just go with a beefy machine. Now to support these layer 2s.
Some questions.
Yeah.
Can we say that layer 2 is also rollup?
No, so every rollup is a layer 2, but not every layer 2 is a rollup. And the difference is going to come to what's called data availability, where the data is sent for, I don't want to get too into the weeds, but let's say you are a rollup only if you settle everything that you need on Ethereum. If you use any other blockchain, for example, Celestia, for specific purposes, you're no longer a rollup, you're a layer 2. So it has some consequences about the security and reliability of the network as well. So rollup is the one that are more closely aligned to Ethereum itself because it uses Ethereum for everything. All right, so to be able to support these layer 2s in a way that is not gonna, again, consume all the network traffic, it was required to have two different ways to store data or to post data to Ethereum. The traditional way was to use block space. That's basically sending transactions to the network that's going to be included in blocks, as we saw in session 1. The other way is to have a new storage mechanism that's called blob space for a specific purpose. So this is the idea, right? You have two, like, imagine two buckets or two databases, block space and blob space. But the EVM, the CPU of Ethereum, can only access one of them. You can only work with the block space, right? And the idea is that every transaction goes to the block space, the EVM processes them and put the result in the Verifiable Computation try. But the blob space, it's a different storage on its own that the EVM doesn't have access to. Another difference is that anything you put in blocks, anything you send as a transaction, you're going to live forever on the Ethereum blockchain. So every single node has to synchronize and store the data permanently. Blob space, actually, whatever you put there, it only lasts for 30 days. So it's like a temporary storage location. And so layer 2s, or rollups that we discussed, they actually make use of both of these for different purposes. So in the case, you're going to see that CK rollup, for example, the validity proof is sent to the block space because it needs to be verified by a smart contract. So it needs the EVM to be able to read it. But then all the data, like the changes in the state transitions, they're sent to the blob space because this is just a way to publish data in a decentralized way. And you don't need the EVM to do anything about that. It's just a way to inform as many nodes as possible of something happening on the network. So benefits is that obviously the block space is expensive, right? So layer 2s are very conscious about what they use the block space for. And block space, because it's only 30 days, it's not permanent, and it doesn't modify or doesn't give access to the EVM, it's actually much cheaper. So the layer 2s actually make more use of blob space for the most part than block space. So there's different fee market for each one of these storage locations. So this blob space was introduced in Q1 2024, and it was created for rollups, actually. But anyone can use it. Even if you're not a rollup, you can still use the blob space for your own use case. And the goal of the blob space is not to store, it is to post data widely, right? And the idea is that if you post this to many locations, then third parties who are interested in that data can actually download it and use it for different purposes, or store it for the long term for a fee if they want to. But that will be now outside of the Ethereum network. The network has a maximum capacity of 9 blobs per block, which gives us a maximum bandwidth of 100 kilobytes per second. It's very low if you compare it with the storage in your computer or the speed of memory and storage. But for a decentralized machine, it's pretty decent. But it also means that we need to be very careful to not overload the amount of information that this layer 2 is sending to the blob space. Otherwise, we're going to crowd again, in this case, blob space, not the block space. Pablo is asking, does this mean that if you don't manage to dump transactions to Ethereum within 30 days, all transactions on L2 will be lost? That's an important distinction. Yes, so everything you put here in 30 days, deleted, removed. That's why you don't put, like, if you're an optimistic rollup, yes, you need to send transaction details to the blob space. So you're relying on a third party, in this case was called the watcher, to actually grab the data and do something with it. In this case, to assess it and create a fraud proof if something fishy is going on. But they only have 30 days to react unless they grab the data and store it in their own database to use later. But yeah, it gets removed. If you want data to be permanent, you have to send to the block space as a transaction. And this is, for example, what ZK rollups do. They send the validity proof that attests to the integrity of the chain. It sends to the block space. Not just because it needs to be verified, but also because for back reference, if you want to synchronize new nodes, you can have all that available to you. All right, so let's go deeper into the difference between optimistic and zero-knowledge rollups. So what is the assumption for each one of them? In the case of optimistic rollup, the assumption is that the sequencer, this machine that creates the blocks for the layer 2s, the sequencer is assumed to be honest until proven otherwise, okay? And this proven otherwise, we're gonna say is called a fraud proof. In the case of ZK rollup, the sequencer's honesty is verified on a regular basis. So you don't trust anyone. You always verify the behavior by crafting a validity proof and sending to Ethereum for verification. So very different assumption about the security of the system between optimistic and ZK rollups. Remember, Starknet is a ZK rollup. Now, when it comes to security, I mentioned that optimistic rollups use a version of ZK technology that's called fraud proof. They're actually quite complex to implement. And that has been one of the difficulties for optimistic rollups, to have a reliable fraud proof mechanism because of the complexity. On the other hand, ZK rollups, what they have is a validity proof, which actually mathematically is actually much simpler to craft and to verify. The other big difference is that layer 1 finality, meaning the time that it takes you to withdraw assets from layer 2 to layer 1 and being able to use it on layer 1, is actually about a week for optimistic rollup, right? So if you withdraw ETH from, let's say, Arbitrum to Ethereum, at the protocol level, you have to wait a week unless someone is willing to run the risk for you in exchange for a fee. That also is valid. But the protocol level, you have to wait a week because that is the challenge period for the fraud proof. In the case of a ZK rollup, because there's no assumption of trust of the sequencer, every few hours, a validity proof that tests that everything that happened in the network in those hours is actually sent to Ethereum and verified. So it means that when you withdraw an asset, you only have to wait a few hours to be able to use it in layer 1. So much faster layer 1 finality. It doesn't mean that when you use one of these rollups, you have to wait a week every time you send a transaction, because you have layer 2 finality and layer 1 finality. It comes into play when you want to withdraw assets mostly. Then what is a block space used for? In the case of optimistic rollup, and actually in ZK rollup, they send similar things. They send, for example, the state roots. This is the root hash of each block created on layer 2. They send what is called messages, the communication between layer 1 and layer 2. And they also send blob commitments, right? Every time you use the blob space, you have to also provide a commitment as part of the block space. And importantly, that's what they send the fraud proof if a fraud is detected. In ZK rollup, it's the same information, but instead of the fraud proof that is sent only when some cheating is detected, is the validity proof that is sent every single time or every few hours. Now, in the case of a blob space, not the other storage that is just temporary, 30 days, optimistic rollups, they have to send the transaction details of everything, every transaction that happened in layer 2, let's say in Optimism or Arbitrum, those transactions, those details, they have to be sent to the blob space. And that is a lot of data, depends on how much the network is being used. In the case of ZK rollups, but it's sent to the blob space, it's just what changed in this global state. If you think about the Merkle-Patricia trie that defines the global state, if you only send what changed since the last time the network was verified or the validity proof was verified. So that is a much smaller amount of data because it's only the difference in state. This is a fun thing that I always chuckle when I watch this video, because it talks about how fast ZK technology evolved and where we didn't expect it. Not even me. Even though I've been working in this field for a while, I was not expecting this to move so fast. And in 2020, I remember Charles Hoskinson, which is the founder of Cardano, and he was involved with Ethereum as well at the beginning. He was asked on an MAM about, what do you think about ZK rollups? And this is what he says, literally. StarkWare dumped a bunch of money into Starks, an academic concept that is going to require a tsunami, a ton of research to get into a practical contract, right? 2020. is that it's going to require years and years and years of hard work to get to a point that these things are practical. Because at that point, we only had like a paper, like a white paper talking about ZK Starks that was published in 2018 by StarkWare. It says, okay, maybe in 5 to 10 years, they'll probably get there. They'll probably have something working out. I thought the same. I thought, oh, this technology is very cool, but it turns out that StarkWare proved them wrong because they launched Starknet mainnet in 2021, just a year later. And we were all surprised, right? Like we all really assumed it's going to take way longer. And the evolution has been so fast that actually now they are better in performance than optimistic rollups, because optimistic rollups were always meant to be like a stopgap. Okay, we know ZK rollups going to take a long time to be there. So what do we do in the meantime? Okay, well, optimistic rollups, we kind of knew the process. Let's go with that. But now ZK is moving at a much faster pace to the point that optimistic rollups are actually now trying to pivot into becoming a ZK rollup as well. Okay, let's see. Any questions so far before I continue here? Talking about verifiable computation.
Yeah, Alexander asked about rollup stage, like the classification from Vitalik.
The CK EVM classification? Trying to find the question.
No, it was in the Q&A, answered. Truth also answered.
Okay.
The last one.
What about roller stage? Okay. Yeah, so at some point Vitalik had a blog post about how to classify different rollups, and he had like a ZK EVM type 1, 2, 3, 4. I think that's it. 1 to 4, I think. And type 1 was supposed to be, okay, this is a rollup that is able to execute exactly every single smart contract on Ethereum can be executed on layer 1. And then type 2 is like, okay, most of it, and then type 3, and some of it. And then type 4 is like, this is like completely different system that is not really compatible with the EVM. And that is the Starknet, right? In the Starknet, you have to use Cairo as a programming language. So you have to pretty much rewrite your Solidity smart contract to Cairo to be able to deploy it to Starknet, which used to be a hassle, right? You have to write the code. With AI now, it's really easy to do. But it really means that it's just a completely different computer architecture from Ethereum. And we're going to discuss why we went down the path, because obviously that creates friction with developers. But there was a very good reason to go down this path. Enrique, no, I think he's talking about Vitalik's blog post. L2b classification is about, decentralization. All right. So let's talk about verifiable computation. Now we're going to get right into how Starknet works and the power of Cairo as a programming language. And I like to talk about this with a story, right? They call it the space exploration problem. I've been telling this story for a long time. Imagine that you're the head of a space exploration agency of a small country, and your goal is to send a robotic spacecraft to Mars, let's say. You have to do some computation, right, to be able to do that, right? For example, you want to save as much fuel as possible, so the spacecraft is smaller, and it's a cheaper program. But you have to calculate, for example, when is the best launch window, like dates, so these planets are close as possible, and what is the best trajectory to get there using the least amount of fuel. And what you do is you give this task to your engineering team, so they develop some program to come up with these answers. And the engineering team will say, okay, let's try to pick up a very high performance language to do this fast because it's a complex computation. Let's say they pick Rust. They could have picked C++ or whatever, but let's say they pick Rust. So what they do is that, they create a program with Rust, but they have an issue, right? This program to run it and to get the answer is so complex that it actually needs a supercomputer to be able to finish in a reasonable amount of time. Otherwise, it will take you, I don't know, months of years to complete. But you don't have one. You don't have one in your agency. It's a small country. Lucky for you, there's a rival country say, hey, I can help. I have a supercomputer that I can lend you, and you can use it. I execute for you and give you the answer. Of course, it's a rival country, so you don't know if you can trust them, but you don't have other options. You say, okay, sure, let's collaborate. So what you do is basically you give them your program, your algorithm. They will execute it for you in their supercomputer, and sometime later they'll say, come back, hey, this is the result. This is when you should launch the spacecraft, and this is the path it should take. And you get the result, right? But you see it there, say, okay, how do I know if this is actually the result? Like, how do I know if this is the output of the program that I gave them? Because it could happen that the supercomputer malfunction and just flip one bit and, the answer is a little bit off. Or it could be because it's a rival country maybe the spy agency just on purpose, they tamper the execution just to give you a result that is slightly off, so you don't really realize, but it's enough to completely derail your program, right? So the spacecraft is going to completely miss Mars, and the program is done. So you just don't have any way to verify that result correspond to the output of your program. And that's the same problem with any programming language, with C++, with JavaScript, with Java. To be certain, you have to re-execute the same thing in a different machine and they start to compare results, right? That's the only way to be certain. But just by itself, you can't. Now, go back in time and let's rerun the same exercise. But this time, let's imagine that the engineering team actually used Cairo as the programming language to create this program. So now you give them the program written in Cairo, the rebel country will execute it. But now what they give you back is not just the result, but also a cryptographic proof of the execution, of the validity of the execution. So now you can actually take that proof and run it through a verifier that you can run in every simple machine, could be just a laptop, a smartphone. And if that proof comes out to be valid from your verifier, you have mathematical certainty that that result is actually the output of your program. You don't have to re-execute anywhere. You just need to verify the proof that was given to you. So if the execution is intentionally or unintentionally modified, the proof will be invalid. That is super important because it allows a regular computer, like a laptop in this case, to keep a supercomputer honest. And it is this balance or this balance of power that actually allows the Starknet to process way more transactions by being supported by Ethereum. So some of the features of the programming language of Cairo, it enables what I mentioned is called verifiable computation, that you derive the validity proof. It runs on top of the Cairo virtual machine, right? Not on top of the EVM, top of the CVM or Cairo VM. The syntax is inspired by Rust. And in the next session, we're going to go actually deeper into the programming language and actually create some programs. So you're going to see the syntax. So if you know some Rust, you're going to actually pick it up very quickly. It has a very similar ownership model. If you know anything about Rust, this is one of the cornerstones of how memory is being managed. It is a strongly typed language. It has traits. It has macros. It can be used outside of the Starknet. So you can use it as a general purpose programming language, not just for a smart contract, which is also an interesting takeaway. And the best of all, you don't need to know anything about ZK to be able to take advantage of or be able to create this validity proof, to have this property that you can convince anyone mathematically that an output is actually what it's supposed to be. So I want to give you an example of this in action. Let me stop there to see if a question. I know Truth is answering one. Any other question, please put in the chat. Okay, Enrique has a question. Generating a proof of my contract's computation in Cairo is computationally expensive compared to optimistic rollups? Yes, because optimistic rollups doesn't create anything. They just assume the sequencer is honest. So they don't have to, they don't challenge it. When you challenge it, is that there's supposed to be a third party watching the transaction detail sense to this blob space in Ethereum. And if it detects something incorrect, like the sequencer trying to cheat by doing some double spending, then that person is actually going to craft the fraud proof and send back to Ethereum for challenging the sequencer. But creating a validity proof is computationally expensive compared to the computation. But it depends. There's a lot of optimization that we're going to discuss for. But if you think as a whole, I'm going to show you a different slide, why this actually, even if you spend more time creating the validity proof, why this as a whole is more performant than just trying to re-execute the whole thing like Ethereum does. Okay, so live demo. I have some Cairo code here. Next week, we're going to go deeper. For now, I just want to show you a little bit this in action. Give me a second to get my guide here ready because I forgot some of the commands. Okay. Great. Let me make sure I don't have, remove this. This was a previous execution. Okay. Cool. So what I have here is a program written in Cairo that has two functions. It has a main function that calls a function called fib for Fibonacci, passes number 16. And then I have a typical Fibonacci function, right? That it calculates, it give me like the Fibonacci of 16, right? And it just does the calculation, returns the value. So I want to execute this program. generate the validity proof, and then verify this validity proof that's going to convince anyone that the actual output of Fibonacci 416 is actually 987. So what I do, I'm just going to open my terminal, and I'm going to I'm going to execute this program. So I'm going to go scarp, execute. I'm going to print the output just so we can see print program output. And we're going to see the output of this, right? So it's going to execute this function, which is called this one. It's going to print the result of this call. So let's take a look. All right, so we see the program output 987. So I want to craft the validity proof of this program execution, right? Like the space exploration thing. So to do that, we actually now call scan scarp proof. So it comes with a prover integrated. All of this is open source. Execution ID. Just because I make sure to remove any other execution, they actually increase in ID. So the first time they run is execution ID 1, then execution ID 2, and so forth. So I'm going to say, okay, you're going to prove this program. It's going to be ID 1. And you know it because if I open here, you go to the execute, you see execution 1. This is what came from the previous command. So I run this. It's going to use what's called the stu prover that is still under development. And now the proof has been generated. And the proof has been stored is here somewhere. It's tell you it was saved to this file, execution 1, proof of JSON. This is the validity proof, right? It's not meant to be readable. This is part of how the system works. So let's leave it at that. And the system also comes with a verifier. So obviously it's silly for me to verify my own execution, but you will give this proof to someone else and they will verify it for you. Like in this case of the exploration program, you will give it to the agency who requested you to execute the program. And then on their own, they will do this scarp verify. Then you give it the same ID. And they will be able to verify. If you see this very quickly, you say, yes, this proof is valid, which convinces you that this 987 is actually the output of Fibonacci 16 without having to re-execute. You only have to verify the proof. Don't worry if you don't understand the details about what is this, what is that. We're going to go into details next session, step by step. I just want to give you a taste of this process of executing, generating the proof, and validating the proof as well. Okay, let's go back to the slides. Any questions so far? Let's see, Enrique's asking, does this affect the Starknet's decentralization? I'm wondering if the fact that validity proofs are more computationally expensive and therefore require advanced specs to run the node prover would be a blocker for anyone who wants to participate in a network validation, limiting to those with enough money to set up advanced hardware. That's a good question. Like I mentioned that to generate the proof, you require more powerful computation. The verification is very cheap. So let's separate those two things. Verification is so cheap that anyone can do it. You don't need any special machine for that. Proving takes more power, but you can see that I just did a proof on my computer very quickly, right? I have an M3 machine with 24 gigabytes of RAM. Like if you want to prove something massive, like the example that I gave you before, yes, you will need to have a more powerful computer. In the case right now of a Starknet, we have one machine that is doing all the proving for all of a Starknet. It's called Sharp. And it is a powerful machine because it not only does all the proving for Starknet, it does all the proving for app chains that use the Starknet stack. It does all the proving for a previous system that's called StarkX as well. But one of the goals with the stu prover, which is the new generation of the prover, is to make the requirements much smaller. This is the first time that actually I'm able to run a prover on my machine with no issues. With the previous prover, actually the one that is currently running on Starknet, it will be much higher computing requirements. So the idea is that these requirements are going to go lower and lower as time goes by. And also there's another frontier, not only to improve the math, which is stu prover is doing, it's also to improve the implementation, to be able to run this thing in a GPU and not just in the CPU, or to have custom-made chips just for proof generation. So there's a whole path for improvement to bring down these requirements down for proving. Verification is super cheap. That's not an issue. Question, do I need to configure any of the files when doing this on Cairo? Don't worry about details. Next session, we're going to go through this step by step. Okay, cool. Right, so we talk about verifiable computation. Now let's go to validity proof, which is what Starknet is using in what I show you that you can generate also locally as well. So how is Starknet using validity proof to scale? So let's go back to the scaling problem that Ethereum has normally, right? So on Ethereum, whenever it is the turn of a staker to propose a new or produce a new block, they will give you the chance to say, okay, you want to propose a new block. It says, okay, I'm gonna pick transactions from the mempool. I'm gonna put in this block. I'm gonna execute these transactions in the block, and I'm gonna propose a new changes to the global state of Ethereum, right? To the Merkle partition trie. In this case, let's say it's 42, just to make it simple. So the block producer proposes a new global state for the network. But what happens is that any other node in the network is not going to simply trust that the block producer is honest. What they're going to do is they're going to take that block that's been proposed, and they're going to all of them execute it individually to verify each one of them that if you execute this block with this transaction, you get to the same global state, that you get this 42 as well. And you can see that this happens over and over on Ethereum and the network and thousands of computers pretty much at the same time or close to it. So you can see that this is very robust, because if the block producer is cheating, someone is going to caught it, right? Someone's going to realize, hey, this person is cheating. And you need to at least 51% of all the validators to be honest for the network to function properly, right? This is important for the 51% attack. But it's very easy to detect if someone is cheating, right? Because all of them are independently executing and comparing results. But this is also very inefficient. You can see every transaction has to be executed thousands of times all around the globe just to get to a consensus. In the case of a Starknet, and same for any ZK rollup, what happens is that the sequencer, in this case Starknet, not only produces a new block, this will be a block for Starknet, not for Ethereum, produces a block, say, okay, if I execute this block, I get this state 42, this new global state for Starknet. Here's the proof, right? So now you don't need to know the details of a transaction. You only need to have the validity proof. So Starknet sends the validity proof to Ethereum as a transaction. So now every single Ethereum validator, what they have to do is simply to run the verification of this validity proof. And if the verification is correct, they know for certain that this is the output is 42 if you execute this block without having to re-execute the block. And I put here just so you can see it like almost like a third, but it's actually a very small amount of computation power. You can see as a whole how the system is much more performant, because you don't have to re-execute the whole thing over and over. You only have to verify the proof, and you are convinced that is the correct new global state for a Starknet. The same goes for any validity proof. People are asking for the slides. I'm going to put it here in the chat so you have it as well to follow along. Okay. Now the next question is, okay, this is it's more efficient to verify than to execute, but how much more efficient? Like how much we are actually gaining in performance? So let's compare. Let's imagine that the work done by the Starknet sequencer is, let's say it's X number of steps to execute all the transactions in the block, right? Now the amount of work that the Ethereum validator has to do to be convinced, basically by verifying this validity proof, is only log square of X. So it's polylogarithmic. So if you put it on a chart, it's easy to see the blue line is X. This is the amount of work done by the sequencer, while the yellow line is the amount of work done by the Ethereum validator to be convinced of the proof. And you can see that the bigger this gap is, the more you gain in performance, right? Because this is the amount of work that the validator doesn't need to do to be convinced that that is actually the output. So this is where the baseline scaling comes from. And this baseline case increases much further thanks to a process called proof recursion that is beyond what I want to explain today, that actually widens this gap even further, making this line even closer to the x-axis. So validity proof is to computation what the zip algorithm is to file size. It is a type of compression, but instead of compressing file size, it's going to compress computation. And that is a very unique property of this new generation. Cairo is a new generation of programming languages that has the property that not many, only a few programs actually have that power. We talk about validity proof, so let's go a little bit deeper about what they actually are. So a validity proof is an implementation, what's called the zero knowledge proof, right? So they take, in the case of Starknet, they case this underlying math of zk Stark or the new version of the circle Stark, and they turn it into a validity proof. But it uses under the hood is a zero knowledge proof. And what it does is that it convinces a verifier on layer 1 on Ethereum of a new layer 2 state transition without sharing transaction details, right? You don't need the details because you don't have to re-execute. You only have to verify the proof. Now, the fact that the transactions of the layer 2 are not shared to layer 1 doesn't mean that Starknet is private, right? It doesn't mean that the transaction is private, because Starknet at the end is an open ledger, just the same way that Ethereum is. There's a block explorer that you can go and inspect transactions. So it's never been about privacy, at least not now. It's been about scaling, using the technology to be able to handle more traffic. You can, however, you can have privacy as layer 3s. That's a thing that is possible. What it does, it makes verification very efficient. And because we use validity proof as the underlying technology, sometimes we like to call, instead of ZK rollup, we like to call it validity rollup, just because ZK sometimes implies that it's zero knowledge, that it's private, and it's not the case really. So you will hear validity rollup as a replacement for ZK rollup. And it's based on ZK Starks, right? This is the math pioneered by StarkWare. There's another family of proof called ZK Snarks, which is different. We're going to see some comparisons later on. And as I mentioned, you get very efficient proven and efficient verification as well with validity proof. Any question? Apparently not. Okay. So if you've been on Ethereum for a while, you probably heard about snarks a lot and maybe not much about Starks. So let's do some very high level comparison of the two. Sometimes there's a confusion because some cryptographers like to say that Stark is just inside the family of the snark, so it's like a parent family. But StarkWare is usually, they see it as a very different branches of zero knowledge. So we talk about compare Stark to Snark. Let's talk about the effort for verifying a proof, right? And the underlying, like the base model, as I mentioned, is polylogarithmic, right? This is the yellow line that I showed you before in the chart. In the case of a Snark, it's actually constant. It's always the same. Doesn't matter how complex the underlying computation is. So that is 0.4 Snark actually. Now the size of the proof, the Stark proof are actually bigger, right? It's like 400 kilobytes or something like that. While Snark is pretty small, it's 300 bytes. So again, 0.4 Snark. So if a Snark is so much better, why did we bother to go with ZK Stark and all this trouble? Well, it's for the next properties. First of all, crafting a ZK Stark is easier than the Snark. It's like an order of magnitude easier to craft the ZK Stark. And that is going to come critical because, as you've been mentioned, at some point it could become a bottleneck, the proving speed, the proving capacity. So having this high performance for proving is really important in the long term. Important for security is that the Stark doesn't require a trusted setup, while the Snark does. And this trusted setup means essentially that the prover and the verifier, they have to share a secret. And if that secret gets leaked, the whole system gets compromised. It means that a hacker will be able to craft a validity proof using Snark that is going to pass as valid even though the person is cheating, right? If this trusted setup is not done correctly. In the case of Stark, there's no issue with that. That doesn't exist. So the point in security. And also very important, Starks are deemed to be post-quantum secure, that even a quantum computer won't be able to break a Stark proof. But we know for a fact they will be able to break a ZK Snark. So that is very important. So we're sacrificing some of these properties, which are important, right, obviously, but we actually care a lot about security in this long-term vision of what the system can do, and it cannot be hindered by these properties right here. And as I mentioned, this gets improved much further thanks to proof recursion. So this is only the base case, but the size is big compared to Snark. Another question that we get usually is like, why did we bother to create our own virtual machine? Why we went with the Cairo VM and not just make it EVM compatible as any other layer 2 seems to be? Well, of course, you have some ZK EVMs on one side, like I mentioned, ZK Sync, Scroll, more, I think, yeah. And then you have like custom VMs, like Cairo VM. Like what you gain on one side is that you get compatibility, right? The ZK EVMs are able to run most Solidity smart contracts without changes, although they often require some small changes because it's not exactly the same, it's very similar. But what you gain, we have in a custom-made virtual machine for ZK validity rollup is that you get the maximum performance of the system. And this is because the underlying architecture of a ZK circuit or ZK CPU, it is not compatible with the architecture of a traditional CPU that the EVM is based upon. This system, they need to have some kind of translation layer to go from some kind of bytecode execution that is meant to be executed on a regular machine that does arithmetic computation to a machine that is based on field elements and that type of computation as well, which is different. So this is why we're always optimizing for the long term. So, okay, we're going to suffer at the beginning because we're going to have to develop all these tools in the language from scratch. But long term, this is the way to go to extract the maximum performance. That's really what you care about, performance and security. I talked briefly about layer 1 finality when we compare optimistic rollup to ZK rollups, right? Like how long it takes for you to withdraw assets. We know that on Ethereum, the finality is about 6 minutes. In the case of optimistic rollup, we mentioned that it's about a week. That's because that's the challenge period of a fraud proof. And we mentioned that in the case of a Starknet, it's about 5 hours that you have to wait to withdraw assets from layer 2 to layer 1. And starting on Monday, there's going to be an update to Starknet that's going to bring down the time that you experience when you use an application on the Starknet. You actually only have to wait half a second to get this called like the layer 2 pre-confirmation. Currently, it's about 2 seconds. It's going to go down to half a second. So the UX is going to get much better. And this is a big upgrade coming on Monday. An example or a proof of this, how much the system can scale. In February this year, we actually had a game that we launched with Cartridge and we ran with the community called Flippy Flop. And the idea was to actually, with the community, do like a stress test on mainnet to see how much further we can push Starknet in performance. Keep an eye. Remember that Bitcoin can only do about 7 transactions per second and Ethereum can do about 15 transactions per second. The Starknet holds, I think it's the record still of layer 2s, handling almost 1,000 transactions per second on mainnet directly. And this is not yet, we have, at that point, we didn't have some of the updates. The Stu Prover is one of those updates going to come online, Cairo native. So even the baseline is now pretty impressive. I think we can actually grow by a 10x more, maybe by the end of this year, to be able to handle even 10,000 transactions per second. So that is massive. That is competing now with Solana in terms of performance, I think, but I'm not a Solana expert. And you can check the stats here. These are the two main block explorers on Starknet, Voyager and Starknet. And we get all this performance at a very cheap price. So this is the average price of a transaction on a Starknet. And you can see that it's way below 1 cent. Like 1 cent will be one here. So this is actually very, very low. So now it opens the door to do way more computation, way more transactions without breaking the bank, right? It's not going to happen like on Ethereum that at some point it peaked to $3, at some point it peaked to $100. It's always below 1 cent. And you can confirm this by going to Growth the Pie and compare transaction costs. Starknet, if I'm not mistaken, the cheapest ZK VM the cheapest ZK rollup of all of them. So to summarize, why Starknet? Well, first of all, it's optimized for ZK technology, for zero knowledge, right? The whole system is meant to be used with this what's called the CPU Air. It gives you more computing power and you pay way less in gas fees, so cheaper computation, but you have more power. It is secured by, it's called ZK Starks plus Ethereum, because we send this proof to Ethereum for verification. What it gives you is a very powerful programming language. We're going to see next session how powerful and how useful the language is. A lot because it's similar in syntax to Rust, so it has some of those nice properties as well. It is a very well battle-tested tech stack, and this is important because you know how many hackers are trying to break the systems. The Starknet has been on mainnet for 4 years, right since 2021, as I mentioned, and that time has secured about $1.5 trillion in transactions and no issue whatsoever. And if you want to withdraw assets from layer 2 to layer 1 or from Starknet to Ethereum, it takes you about 5 hours, and there's no trusted setup. So there's no risk of the system being compromised by a secret being leaked. And of course, it's post-quantum secure as well. Okay, so we talked about layer 2s, optimistic versus rollup, verifiable computation with Cairo, validity proof, how's that helping to compress computation, some comparison between Starks and Snarks. And now let's go to the next topic, that is smart wallets. So what is a smart wallet? So it is a wallet that will allow you to, first of all, for example, sign transactions with your Touch ID or Face ID in your Apple, or you have an Android as well with your fingerprint. And that is because it's able to use the dedicated cryptographic system of your smartphone compared to what's called an EOA, which on Ethereum, if you know MetaMask, for example, MetaMask is an example of an externally owned account, or EOA. On Starknet, there are no EOAs. Everything is a smart wallet. You can also execute multiple operations in a single transaction. Basically, you sign only once and you do multiple operations. With an EOA, you will have to sign each transaction independently normally. As I mentioned, on Starknet, every wallet, it is a smart wallet. They all implement what's called the account abstraction pattern, which makes the wallet much more useful and gives you a much friendlier UX as well. There are no EOAs. And the main two providers for wallets are actually, it's no longer called Argent, it's called Ready now, and Braavos. And I'm going to be showing you how to set up a wallet in a minute. But you can also use, you can use Ledger with Braavos as well if you have a Ledger. You can use even MetaMask with an extension. I think it's also possible to use Starknet. But if you want the best experience, really go with Argent, or what's called now Ready, or Braavos. I mentioned that one of the benefits is that you can bundle multiple operations in a one transaction. That's one of the benefits of this account abstraction pattern. So let's show you how it works. Imagine that there's some flow that requires you to sign two transactions, or normally we require you to sign two transactions, one for step one for step two. The very common scenario is when you want to use some DeFi protocol, you usually first have to approve, like allow the smart contract to spend some of your tokens for you, and then actually do the operation you want to perform. It could be a swap, for example. Normally there will be two steps, right? Two transactions you have to sign. And the issue with that is that, not because if you execute those two transactions in certain order, there's no guarantee that those two transactions will actually make it into the same block and in right next to each other, right? Because it could very, very well happen that they actually get included with a transaction in the middle from someone else, or they may actually get included in different blocks, right? You have no control over that. And the downside of this is that you are vulnerable of a type of economic attack called the MEV, maximal extractable value, where I'm not calling it a hacker, but an entity will try to extract some value from your transaction, extract value from you. Like, for example, change the spread of the trade that you want to do and get some money from you to their pocket by just inserting transactions in the middle of your flow. And this is very common. It happens all the time because you don't have control of this, essentially. And because these operators, they're always checking which transactions are going to the mempool to try to front run or do sandwich attack or do anything they can. A benefit of being able to bundle these two operations into a single transaction, which you can do on a Starknet because it has a feature called multi-call. You can bundle all these operations into a single transaction, is that now you have total guarantee that those two steps in the flow, they will actually get executed in a single block and with nothing in between, right? Because they are now essentially one transaction with two steps in it. So it gives you some level of protection against some types of MEV attacks, not every type of MEV attack, because they can still front run your trade, but they won't be able to get something in between your execution, right? So that's one benefit. Another benefit is that it will make the whole operation cheaper, because the fact that it's now a single transaction, not just with two steps, you can imagine one having 100 steps, right? Instead of having 100 transactions, all of them with their own overhead of signature verification, blah, 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 it will be only one transaction. So the overhead is less. It means that the same amount of operation will be cheaper. I mentioned that this is possible, that the fact that we call on Starknet every wallet to be a smart wallet is because all of them follow this kind of abstraction pattern. And what this pattern does is basically to decouple the signer from the account, right? because normally in the EOA or MetaMask, those two things are the same thing. And now the signer is the entity that is gonna sign transactions. They're gonna identify you with a private key. And the account now is actually a smart contract that is stored on the network, on the Starknet, and it's going to be the thing that actually holds the assets, right? It's the thing that's going to verify the signature coming from the signer, and say, okay, if the signature is valid, I'm going to allow this signer to actually take control of the assets. And it's also the smart contract, the one that performs the multi-call, this thing that you can bundle multiple operations into a single transaction. And yes, Alexander, I saw in the chat that say, you're right, it doesn't protect against all MBB, but it just protects about transactions being included in the middle. I mentioned that sandwich or front running is still possible. So a kind of structure in practice, right? Like how does it work at a high level? So now that we have the separation of the signer and the account, in this case, we call it the account contract. It's just a smart contract. It's a smart contract that just follows a specific interface, right? And in Cairo, we define interface with traits. And this interface is defined by standard, we call this SNP6. So if you see a smart contract that has these functions and they comply with the SNP6 standard, we know that that smart contract is not just any smart contract. It is an account contract that is tied to one or multiple signers. It's meant to be used to control assets. So what happens is that, let's say you want to interact with some target smart contract, right? So what you do is that your signer, usually your device, your secure enclave, is going to sign a transaction and it's going to send it to your account contract. There's always going to be an account contract like attached or associated with a signer. And now it is the account contract that's first going to validate the signature. And if it's valid, then it's going to execute. It's going to be the account contract, the one actually interacting with the target contract on behalf of the user, right? So you see now the separation of the signer from the account. And this is just smart contract that follows certain interface. The verification of the signature, basically verifying the signer, is also, it is programmable. You can define the logic behind that. And this is powerful because if now it's programmable, it means that you can define an account, in this case, a wallet, that can have, could be a single signer, which is like the most common use case, or it could have multiple signers, like a multi-sig, but in this case, supported at the protocol level. You could have a hardware signer. So instead of signing with software, like MetaMask would do, you actually sign with a specialized hardware in your computer or in your smartphone because it supports certain elliptic curve. You can do social recovery. So in case you lose access to your seed phrase, you can define guardians that will give you access to you, like some friends, family, or whatever. You can have session keys. So when you play, let's say, a game, in the game supposed to do multiple transactions, you don't have to sign every single transaction all the time. You delegate to that signing to the client, to the game client for a limited period of time for a limited number of assets. That is very common. You see it a lot on a Starknet as well, session keys. And also another benefit is that the Starknet supports multiple elliptic curves. It supports one's called the Stark-friendly elliptic curve. It supports the elliptic curve used by Ethereum as well. That's why you can use Ledger to sign transactions on the Starknet. And it also supports what's called the standard elliptic curve used by your smartphone and your laptop as well. So this is, for me, one of the most interesting things about this account abstraction is the fact that you can use the secure enclave of your smartphone to sign transactions. So in a way, it kind of turns your smartphone into a sort of hardware wallet. Somewhere in between, right? I'm not going to call it, it's not as secure as a ledger, but it's much secure than the status quo of just using the shared system. Because in any modern smartphone, you have two subsystems in your phone. The shared system is the one that has like the biggest processor, like pretty much all the memory. Like when you see the specs on your phone, what you're really looking is at the spec of the shared system. And then there's a smaller subsystem that is going to have its own processor, it's going to have its own memory. This is normally not too, it's not part of the marketing of the company because it's only done for very specific purposes. So the shared system is where the OS actually lives, your Android, your iOS, and where all the applications get installed to, right? They all share the processor and the memory. This is why when you have a wallet, like it lives only here, it's a little bit more risky because now some of the resources have been shared with other apps, and there is a malicious app installed, it can potentially have access to that shared memory. But now, if you're able to access secure enclave, this secure enclave, what it does, it has very specialized functions. If, for example, it's able to generate numbers, random numbers, which is hard to do, really, random numbers. It's this system that manages all the cryptographic keys of the system using for signing transaction. And when you sign a message or a transaction, it will do it with specialized hardware in using the what's called the standard elliptic curve, the R1. And this is whenever you use keychain or Touch ID or Face ID or your fingerprint, they actually are all using the secure enclave, right? So this is the most secure part of your system. So this is the benefit of the account abstraction method, that because now you can define that your account contract supports this type of elliptic curve, which is the standard one. Now you can have wallets that actually are able to use Touch ID or Face ID to sign transaction using this limited system and just directly with the hardware. And when you see, I'll show you how to install Braavos, you're gonna see that in action. And we're gonna use, in case I have an old Android just for this test, is something similar to a Touch ID. Of course, the system, the secure enclave, is the name for Apple. The generic name is the TEE, the Trusted Execution Environment. Secure enclave is the name that Apple gives it, but you have a Google Pixel, it's called Titan M. If you have Samsung, it's called Knox. In any other ARM-based machine, it has a system called Trust Zone. And this also applies for laptops, right? Because modern laptops, you can also have a fingerprint reader. Question from German. Are there any security, performance, and resulting gas disadvantages of using AA? Seems like it requires more computation on chain and more contracts involved. Gas disadvantages compared to what? Because every single wallet uses account abstraction, so I don't know. If you compare against EOA, it's hard to compare because there are no EOAs on Starknet. The only thing I can mention is that it will depend on. I mentioned that you can program how complex or how system this logic is going to be, right? And this is a good point, because if your logic is very complex, like the one that you put here into the validate function, yes. So now every single transaction is going to be a bit more expensive because now they all have to pass through a more complex validate mechanism. But what you gain is that whatever you implement is automatically supported by any smart contract on the network, which is different from Ethereum, that you have a support for EOAs is much better than support from multi-sigs doing the old-fashioned, and then support from the account abstraction wallet still somewhere in the middle because it's newer. You don't have that issue with Starknet. Everything is in account abstraction. Everything is supported by default because the target smart contract is oblivious of the logic that you define your validate. It's not its responsibility. It only cares that someone is trying to access its internal storage. Hopefully that answered the question. All right, back here. Okay, smart wallets. Benefits. So you get a much better UX than regular wallets because everything is programmable and support is a first-class citizen. As mentioned, you have like multi-call, you have hardware signer, you have social recovery, session keys, etc. It is enabled by account abstraction, this mechanism that I mentioned, separation of signer from account. And the account is simply a smart contract with a specific interface defined by standard, the SNP6. And it supports signing transactions with different elliptic curves. I mentioned you can use the Stark friendly, you can use the Ethereum curve, you can use the standard curve as well. And on every wallet on a Starknet, it is a smart wallet. There are no EOAs. Alexander mentioned we also have the Experts wallet. That's very true. That is a new, recently wallet that actually now has support for Starknet. Thank you. I need to expand my slides. All right, time to give you an example of how to install a wallet. And what we're going to do, we're going to install the Braavos mobile app. I'm just going to use Braavos and not all one just because it's a bit easier to do in the time that I've allocated, but you feel free to use it with Experts or some other wallet that supports Starknet. We're going to set up the account with two-factor authentication. So whenever we sign transaction, we're going to use it with the secure enclave or the TEE. We're going to, if you have time, install the browser extension, and we're going to also claim the SPOC. So let's do that now. Let me exit here. And I'm gonna have an old phone here for this demonstration that I need to unlock. Okay, it's unlocked. I'm gonna bring the terminal so I can do strcpy. Hopefully this will do the screen sharing for my phone. Yes, it is here. Okay, hopefully you can see it. All right, let's put it here. Great, so this is my phone. So I mentioned there's a multiple wallets. If you go to the store, sorry, in this case, I have an Android device. I mentioned there's the Ready wallet, Ready wallet Starknet, right? This is the one you can use by Argent Labs. You mentioned also Xverse group. Oops. You can actually flip this like this. It's crazy. You have the Xverse wallet, which is a Bitcoin wallet that now also supports Starknet. Another good option, this one right here. You can use that. And the one I'm going to be using today is called Braavos. So let's go with Braavos wallet. And is this the one? Just make sure there's no other. Yeah. All right. So Braavos supports not only Starknet, it also supports Bitcoin. So you can have a wallet that supports both, similar to what Xverse does as well. So I'm going to install this one on my device. If you do this with me, or if you have a wallet already, you're going to be able to claim a SPOC right after. So I'm going to open the wallet. I'm going to create a new wallet, but if you already have a seed phrase, you can actually import this as well. One point to mention is that the seed phrase, it's not compatible between different wallets as far as I know. Like this is it has to be a seed phrase coming from a Braavos wallet. It cannot be a seed phrase coming from a Ready wallet. If you have a seed from a Ready wallet, you have to insert it into the Ready app. I'm gonna create a new wallet here. This is the password to unlock the system. I'm just gonna something simple. I'm just gonna delete this wallet afterwards. Just gonna call it Basecamp, whatever. Just make sure that in your case is something safer and not revealed. And unlock your wallet with your biometrics, right? Enabled by default, that's good. Let's go and next. So at this point is generates the seed phrase for me. I'm going to simply click copy. Make sure that you save it. I'm not gonna save it just because I'm gonna remove this wallet as soon as we're done, but just make sure that you store yours in a safe place, write it down on a piece of paper and just write that somewhere. I'm gonna go next. And very important, if you want to use the secure enclave, in my case I have an Android, so it will be the Knox because Samsung, or the trusted execution environment, you have to enable that option. So protect your Starknet account using 2FA hardware signer. So this is going to use the secure enclave. When I click next, so that's going to pre-configure on my account contract that Braavos is going to generate for me. And okay, next. And that's it. So in theory, my wallet has been deployed. What's happening here? Finish 2FA setup. What did I do? Oh, you didn't know what's happening. Decline. Let me see what's happening. Turn some fine here. If I go to security, the hardware signer seems to be enabled. That's fine. Okay, I think it was just processing the transaction in the background still. You can see that I have two wallet addresses, one for Starknet protected by 2FA, and one for Bitcoin as well, right? So now the next topic is going to talk about this integration with Bitcoin, but you can see that now multiple wallets support Bitcoin natively as well, Xverse being one of them as well. And Ready don't directly support Bitcoin, but you can directly swap Bitcoin to Starknet using Ready as well. So if I copy this address, you can see if I go to a block explorer, Like if I go, for example, StarkScan, and I copy this, you can see it's an account. It's a smart contract identified as an account. And if I take a look at the API, you can see some of the functions I was mentioning before, right? Like the validate, yes, is valid signature, validate deploy, validate declare, and also execute has to be here somewhere, or maybe this one is internal. That one is internal. Yeah, some functions are just internal, so are not exposed here, right? Oh yeah, validate and execute, right? So you can see the SNP6 that I mentioned is implemented in this smart contract. That's why it's classified as an account contract, and it's the one assigned to the wallet I just created. So if I go back here, what happened to the wallet? Go back, I close this. What I want to do now is I want to claim a Spark. Oh, I want to show you how to import this wallet on your browser extension, because one benefit of Braavos is now they actually cover all the fees, all the transaction fees that you do on the wallet, on the mobile wallet, not on the browser wallet. So this is free because they use a system called Paymaster. So if I want to have it in my browser, what I need to do is I go to the extensions. Let's see, what extension do I have? I don't have anything here. I'm going to install here the Braavos extension. This is an extension for my, in this case, Brave, but it's the same for Chrome. It's a Chromium based. So I'm going to install this. I'm going to add the extension. Right, it is installed. Let me make it visible all the time. So now it's asking me the same question. Okay, do you want to create a new wallet, or do you want to import the seed phrase? So now I have a wallet, right? I have a seed phrase. So let's use that, because I want to have the same wallet on my phone and in my browser. So I'm going to go import seed phrase. I'm going to do this live just because I'm going to remove this wallet. So be careful when you reveal your seed phrase. This is not the case. Wallet settings, privacy and security. Show secret recording phrase. Yes, this one I'm looking for. Again, don't do that live. Be careful. Just do it in a place that I don't see. I'm just going to copy this seed phrase, and I'm going to put it here. Next. The password can be different. It doesn't need to be the same as you have in the phone. Just going to put the same just for simplicity. And now it's doing the recovery of the wallet, and I should be able to see the same address on both my phone and my browser extension. So it's cool to have that system check. So now every time you send a transaction, even when you use your browser wallet, it's going to ask your phone, it's going to ask you for confirmation using your fingerprint or your Face ID. So that is the two-factor authentication in practice. Go ahead. Oh, here it is. It's done. Okay. Starknet. Great. Let's talk about Bitcoin. So the plans to the integration. So performing dual settlement. So the idea here is that Starknet wants to become the first ZK rollup that is able to settle on Ethereum and in Bitcoin, right? We're not going to abandon Ethereum. We're just going to extend to Bitcoin as well. And today what we do, we send the validity proof to Ethereum, and thanks to that we have this trustless bridge, so we can move assets natively between Ethereum and Starknet. But also we have the security of Ethereum on Starknet, and the goal is to have the same benefit now with Bitcoin. So we're going to be able to send the validity proof both to Ethereum and to Bitcoin. So it's going to be verified by a proof of stake network on one side and by a proof of work network on the other one. And that will also give us a native bridge to bring Bitcoin into Starknet alongside with Ethereum and any other token that exists on Ethereum as well. And that is a big deal. And so what are the benefits? So the main benefit for me is that it will create finally a trusted bridge between Bitcoin and Starknet, which is going to allow us to have finally real Bitcoin and not just some wrapped version of Bitcoin that is supported by a third party that can rug pull you at some point. You will be able to do faster Bitcoin transactions on L2. We mentioned that Starknet can handle today 1,000 transactions per second. Very close, it's going to get to 10,000. And I show you that the fees are extremely low, below 1 cent. So because it's going to be so cheap and so fast, it actually can become an alternative to Lightning, to a Lightning network, right? And Lightning only allows you to send and receive Bitcoin, but in Starknet you can do way more. You can do, for example, DeFi, so you can earn a yield on your Bitcoin while using it as a payment mechanism as well. And if we manage to bring this liquidity to Starknet, one benefit of having more liquidity is that all these DeFi protocols, they become more capital efficient, which is a better deal for users at the end as well. And I think important for people who are more Bitcoiners, more hardcore Bitcoiners, is that when that trusted bridge is set up, the benefit is that your Bitcoin on Starknet is going to be secured by the proof of work network of Bitcoin and also by Ethereum as well, right? But it is important that if you really are a maximalist of Bitcoin, to know that the system is ultimately secured by Bitcoin itself and also by Ethereum with this trusted bridge and with ZK, zero knowledge proof. So how can we make it happen? The different ways. They have three mechanisms, right? First one is to use BitVM. Second one will be to use something called Collider VM. And the third one will be to use OPCAT. So let's take a look at the first one. So with BitVM, which is a protocol, is not developed by StarkWare. There's another group developing that for Bitcoin for multiple purposes. The idea is that the Stark proof or the validity proof is going to be assumed valid unless challenged by a third party during a 1 week dispute period, right? That is at a high level how it works. So it's kind of like a hybrid between a validity, fraud proof or optimistic rollup, but at the bottom of it is actually a validity proof being assumed as valid, not just the sequencer. So the pros is that we will have a trust minimized bridge with no need for a soft fork of Bitcoin, right? So no need to go through this whole discussion. And BitVM seems to be close to launch. So it's something that we can potentially have ready quite quickly once BitVM becomes ready. Some of the negatives is that, being similar to an optimistic rollup of sorts, you're going to have this long dispute period of 1 week. You can do it faster if you want, but you're going to require a third party to provide the liquidity up front. So there's going to be some capital inefficiency there to make it faster. So there are pros and cons. The other avenue of research, and this is a research actually conducted by StarkWare themselves, is to use a system called Collider VM. And the idea of Collider VM is that the Stark proof is sent to Bitcoin and verified on chain with a custom virtual machine using Taproot scripts, right? So different trade-off. Again, benefit is no soft fork. It can be implemented without reaching consensus with the community. And also benefit compared to BitVM, no dispute period, right? As soon as the proof is sent and verified, it's done. The downside is that this Collider VM is still under development. It's very young. The research needs a lot of time to optimization. Maybe I'm being Charles Hoskins now, thinking it's far away, but actually it might be closer. But this is a StarkWare is working very hard on. But also challenge is that it requires some complex off-chain computation because it requires some partial hash collisions. So again, trade-off. And the ideal version of this, it will be to have OPCAT re-enabled on the Bitcoin network. This is an opcode that existed at the beginning of Bitcoin, but it was removed. But if we have to have it re-enabled, the benefit is that we're going to be able to have a Stark proof sent to Bitcoin and verified on chain using directly just Bitcoin script. So no magic of Taproot scripts or complications, just Bitcoin script, and the proof can be verified. So this is the best. This is actually a trusted bridge because now you have complete on-chain verification. It will use native script logic of Bitcoin. The main downside is that it requires a soft fork. So the whole community of Bitcoin needs to agree that it is safe to re-enable OPCAT into the network. And this is something that will take a time and it's been discussed. So what is this OPCAT opcode? What is so important? But what it does? So at a very fundamental level, what it does is just concatenates two values in the stack. That's really all it does, right? But this is important because a Stark proof I mentioned is a big one, right? It's not a small thing, it's 400 kilobytes. So it doesn't fit in a single transaction. You had to break it down into multiple transactions. But right now, Bitcoin script can only have context on a single transaction to operate. With OPCAT, you can now give a Bitcoin script access to more than one transaction in its context of execution. So now I can potentially execute on the verification on a big Stark proof that exists into multiple transactions. With that, the benefit is that Bitcoin Security will be able to verify a Stark proof. Now, this opcode was removed or disabled in 2010 as a precaution for a denial of service attack. Of course, it's a very different Bitcoin network from 15 years ago. The network has evolved a lot since then, even though slowly, but it has evolved a lot. So this re-enabling is under discussion, right? And you are going to some meetups, some discussion events, and it comes back. I don't think the community is ready yet to do this enabling, but it's being considered. Some other opcodes might be enabled first. I mentioned it requires a soft fork of Bitcoin, meaning an upgrade to the protocol itself, which is not easy to do. So BitVM, that's why it's a viable alternative, because it doesn't require this soft fork, and CollectorVM is being researched as well, as I mentioned. This is an example from Abdel. He works at StarkWare, showing how would this actually work in practice. So basically, they set up a testnet for Bitcoin, showing how you can break down the Stark proof, send it to Bitcoin and verify it. I think we can play this video here. So basically, what he's doing is starting running some computation with Cairo, and then it's gonna create the proof, and then the proof is gonna be divided into, I think, a lot of transactions. I think like 70 transactions. Send all of them to Bitcoin, and then with OPCAT, because this is a signet that it has OPCAT enabled, right? So just as a way to test how this will work. So now this is going to be a script with OPCAT enabled that's able to grab all this transaction that has the Stark proof and do the verification on all of them. So that's why you verify the proof. So you can see here all the transactions being sent to the network into multiple transactions. Could be in the same block. I think it will be all in the same block. It takes a while. It's processing. I'm just gonna leave the video play. It's not long, so it's just 1 more minute. You can see. Let's see what else is showing. It's all the setup, the system, and at some point you're gonna see the transactions going through. Okay, creating program transactions, setup complete, and then here you see running a main demo. The transactions 1, 2, 3, and a lot of them, 72. You can see the number. So it's a big. Star proof are big. So it's not going to be cheap, right, to send all these transactions. But if you're able to batch multiple layer 2 transactions into a single proof, you can spread out the cost into all of them. So the average cost will still much lower than doing the transaction on Bitcoin directly. And you can see now all the transactions has made it to the block, and the verification has been completed. So the proof of work, the proof of concept is actually here to showcase that it actually will work. Back to slides. So one of the concerns about OPCAT is that it will potentially give too many new powers to the network and maybe have some unexpected consequences. At StarkWare, they believe that is not really a concern anymore, because the network has improved a lot. Some of the security has been improved. But to give peace of mind, they actually set up a 1 million fund for any researcher who wants to put OPCAT to its spaces, to try to find any vulnerability, any way to attack Bitcoin with OPCAT to show, hey, it's actually dangerous, or hey, it's actually safe to use. So that fund is still open, so anyone who wants to research can tap into it. And just the idea is to bring peace of mind to anyone who's concerned that OPCAT might actually open the door for something dangerous for Bitcoin itself.